Hello student, how are you? I'm Arun sir. Welcome to my channel Tuition Expert. Today's class is on heat engine, Carnot engine and refrigerator and second law of thermodynamics, reversible and irreversible process. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the iitjee exam and NEET exam confidently with a good rank. Now let's start about the class. So heat engine, there are two types of heat engine: external combustion, external and internal combustion. External combustion heat engine, internal combustion. Okay. External combustion example: steam engine. Steam engine. Internal combustion engine, diesel engine, petrol engine. Diesel engine, petrol engine. So this is ICs, abbreviately IC engine. Old train where fuel is combust in outside. Fuel is combusting outside, and diesel engine fuel or fuels petrol, and here petrol and diesel is combust in within the instrument. Fuel is combust within the instrument. So a IC engine simple diagram is, what is IC engine? Here a cylinder main, a cylinder piston is present. In every IC engine a cylinder piston is present, and in a separate chamber petrol or diesel is combust. This is the chamber where petrol and diesel is combust. That is, here combustion of petrol and diesel is performed. Now when petrol and diesel is combust within a chamber, then high pressure gas is produced. This high pressure gas is entered into the cylinder piston system. Here is a valve present. So this is simple diagram. Complicated diagram is present. Just I show the simple diagram. Here a crank mechanism is present. This is cylinder, this is piston, this is piston, this is cylinder, and a crank mechanism. Suppose this is a rod and this is a rod. This rod is connected by rod, and axle is axle means where the rod at which the wheel of the car is joined. This is the wheel of the car. Car is joined through a rod, and this is the wheel of the car. The wheels are joined through a rod, and this rod is connected at here. So when the high pressure gas pushes the piston, then it exerts a force. So this moves upward, and when it reaches at certain height, then this valve closed and this valve opens. So pressure falls. So due to weight of the piston, now this comes. Again the cyclic process repeat. So this piston moves up and down in this way, and this rod that is this axle, that is rotates in a circular manner this way. So this way high pressure gas is produced, the motion. This way heat produces the motion of the car. So this is a simple diagram of an every IC engine. Now surrounding is air. We know the that is hot gas is ejected from the every IC engine, and this is ejected to the air. So air is called here surroundings, and this is called also sink. Air is here sink, and petrol, diesel, here heat is produced. This is called source. So this piston moves up and down and performs a cyclic process, this and this. So every IC engine there are things. One thing is source. So every IC engine, two main things is present. One is source. Here source is petrol and diesel combustion chamber, whose temperature is T1, and here heat is introduced, that is heat from the source is introduced through a chamber which is cylinder piston chamber. Cylinder piston, here piston moves up and down and performs a cyclic process. So the process is cyclic, and some unused gas ejects to the air. So air is called here sink. Air is called sink, and this maintains at temperature T2. Now always to perform the IC engine or cyclic process, T1 must be greater than T2. T1 must be greater than T2. Sink, that is air temperature is less, and source temperature, that is this temperature of the gas of petrol and diesel in combustion chamber, is more. Now, so heat is introduced to the chamber, and some heat is rejected to the sink. What is the result? The result is that some work is done by the piston. Some work is done by the piston, or if we call this is machine, some work is get from this machine. So this is what done. Now some heat is introduced to the chamber. This is called Q1, and some heat is rejected into the sink. This heat is Q2. So Q1 amount of heat is introduced to the cylinder piston chamber, which performs in a cyclic process, and some heat is rejected to the sink. This is Q2. So result, some work is done by the machine. W is some work done by the machine. Here, what is important term? Important term is efficiency. We have to find the efficiency of the heat engine. Efficiency of heat engine, which is equal to output work done by input energy. Output energy by input energy. For efficiency for a cycle, for one cycle, efficiency for one cycle equal to output energy in one cycle divided by input energy in one cycle. Now what is output energy? Output energy is work done. This is work done. Output energy is work done, and input energy is Q1. Input energy is Q1. W by Q1 is efficiency. Now here, what is the relation between Q1, Q2 and W? Now input is Q1, so Q1 equal to input. If you consider this system, here Q1 is inputs and two outputs, Q2 and W. So Q1 equal to Q2 plus W, and W equal to Q1 minus Q2. So if you put W equal to Q1 minus Q2 divided by Q1, which is equal to 1 minus Q2 by Q1. This is the answer. Now 1 minus Q2. If Q1 here, heat is proportional to temperature. Heat supplied to the system. Heat supplied to the system from the source is proportional to temperature of the source. So Q1 is proportional to T1, and also Q2 is proportional to T2. So Q1 by Q2 ratio will be T1 by T2. 1 minus T2 by T1. So Q1 by Q2 by Q1 is proportional to T2 by T1. 1 minus T2 by T1. So this is the answer. Efficiency equal to efficiency of an engine for a cycle. So this is the result. Efficiency eta for one cycle is 1 minus T2 by T1. T2 is less than T1. T2 is the sink temperature, T1 is the source temperature. T2 equal to temperature of sink, which is here, which is air or surrounding, temperature of sink or surrounding air, and T1 is temperature of source. Here petrol and diesel chamber. Petrol and diesel chamber. Okay. So this is the formula. Efficiency equal to 1 minus T2 by T1. Efficiency equal to this. T2 is temperature of sink, T1 is temperature of source. Fine. Here problem is very easy. Problem very easy. If you remember, if you memorize this formula and what is this T2 T1 and T2, what is T2, what is T1, what is efficiency, you can solve the problem related to IC engine very easily. Okay, now I give the one example. So in a Carnot engine problem, in a Carnot engine, suppose this is a Carnot engine is ideal heat engine, a ideal heat engine. I will discuss Carnot engine later, but this is actually heat engine. So you use the formula of heat engine. An ideal heat engine in a Carnot engine operates with an efficiency of 40% with its sink at 20 degrees and by what amount should be temperature of the source be increased with an aim to increase the efficiency by 10%. Suppose this is the problem 1, problem related to heat engine. So what is the question? In a Carnot engine, ideal heat engine operates with an efficiency of 40% with its sink at 27 degrees centigrade. By what amount should be the temperature of the source be increased with an aim to increase the efficiency by 10%? That is, next efficiency will be 40 plus 10, 50%. So you have to remember the language, 10% more. Now initial we know, so if you cannot remember the formula, just you remember the diagram. So this is source whose temperature is T1 and Q1. This is the cylinder piston chamber. In the cyclic process, work is done by the machine and some heat rejected to the sink temperature is T2. So you remember this diagram. Okay, then you can establish the formula yourself. So what is the efficiency? We know the efficiency equal to output by input. From class 10 you have learned that efficiency equal to output by input. Now what is output? Output equal to, here work done is output. So W by input equal to Q1. Now what is the relation between Q1, W and Q2? Q1, we here see that Q1 is input and 2 output, W and Q2 is present. In an ideal engine we always know that efficiency is 1, that is, we always know that if input equal to output, if no energy is lost, then we can say that input equal to output. So Q1 is input and total output is W plus Q2. So W equal to Q1 minus Q2. Now put here W equal to Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1. Now 1 minus Q2 by Q1 equal to T2 minus T1. So if you cannot remember the formula, you have to you can establish the formula yourself. If you remember this diagram quickly, just remember this diagram, you can solve more easily. Now efficiency equal to 1 minus T2 by T1. Now what is the sink temperature? Sink temperature equal to 27 plus 273 Kelvin. Here T2 and T1 is always are in Kelvin scale. T2 and T1 are in always Kelvin scale. No, not degree centigrade. Always Kelvin scale. So this is very important that T2 and T1 are in Kelvin scale. So you have to convert from degree centigrade to Kelvin scale. Now what is the relation? 0 degree centigrade equal to 273 Kelvin. So 27 means 27 plus 273. So efficiency equal to first 40 by 100 equal to 1 minus T2 is equal to 300 by T1. So 2 by 5 equal to 1 minus 300 by T1. %10 more. Second efficiency will be 40 plus 10, 50%. So from this we get 300 by T1 equal to 1 minus 2 by 5, which is equal to 3 by 5. So 3 cancel, 100 and 500 equal to T1. So initial source temperature is 500 Kelvin. Now in second step, again efficiency for second efficiency will be 40 plus 10, that is 50%. So again we use the formula efficiency equal to this formula 1 minus T2 by efficiency equal to 1 minus T2 by T1. Now the source temperature is suppose T1 dash. So efficiency equal to 50%, 50 by 100 equal to 1 minus T2 sink temperature remains same, which is equal to 300 by T1 dash. So here from this we get 50% and half equal to 1 minus 300 by T1 dash. So this is the temperature of a heat engine. A heat engine rejects 75% of the heat. 75% of the heat supplied to the surroundings per cycle. Find the efficiency. Problem 2. So if you cannot, the problem is a heat engine rejects 75% of the heat supplied to the surroundings per cycle. Find the efficiency of the heat engine. So if you cannot remember, draw the diagram. This is source. So if you draw the diagram, this is source. This is source whose temperature is T1 Kelvin, and water. This is a sink. Temperature is T2. Okay, Q2. This is source. This is sink. Source, sink, T2. You have to remember this diagram also. Okay, to solve the problem related to heat engine. Now what is the efficiency? Efficiency equal to 1 minus T2 by T1. I have established this 1 minus T2 by T1. So 1 minus. Now here efficiency heat engine rejects 75% of the heat supplied to the surroundings. 75% of the heat supplied to the surrounding. Now this is 1 minus Q2 by Q1. So 1 minus Q2. Now Q2 is giving rejects Q2 equal to 75% of the heat supplied to the, so Q2 equal to actually 75% of Q1. This is given. Okay. So just study the language. Just study this language. Rejects 75% of the heat supplied to the surrounding. 75% means 75 by 100 into Q1. 75% of which 75% of input, that is Q1, divided by Q1. So this cancel, 3 by 4, 3 4. So 1 minus 3 by 4 means 1 by 4. So efficiency equal to in percentage form into 100, that is 25%. This is the answer. Now refrigerator. Refrigerator is a system which absorbs the heat from the sink. Refrigerator is a system which absorbs heat from the sink. So which contains some ammonia plus freon etc. type of substance whose temperature is very less, minus 20 degrees centigrade around, contains in a chamber, in a tube, in a fridge or refrigerator. Cold gas is present in a conducted tube. Actually, refrigerator works along the reverse direction of heat engine. Okay, that is, direction should be reversed. That is, refrigerator system which takes the heat from sink to the source, which takes heat from the direction of heat flow from sink to hot floor. Generally instantaneously but automatically heat flow from hot body to cold body, but here in refrigerator heat flow from cold to hot body. So generally spontaneously heat cannot flow from cold to hot body. So an external work must be done on the refrigerator, which is in fridge or refrigerator, compressor is the instrument which externally works on the refrigerator and the heat flows so that heat can flow from cold to hot body. In refrigerator, suppose this is a fridge, home fridge, here or cold gas is contained within a copper tube, within a copper tube which is not seen, it is covered at the top. It is covered at the top so that it can this U2, and in the back side of the fridge a compressor is present backside, that is at this point. Compressor is a system which operates the gas contained in this tube in a very quick process. The compressor is an instrument which runs the gas in a cyclic process, and that is a work is done by the compressor. So here a chamber is present. Now here the things is present. Here the object of things, object fruits or food etc. is present here. Now this is here, and this space is called here source. This is source, and it is called the sink. Here sink is at here and source is at here, and work is done on the sink by compressor. So the diagram becomes, suppose this is a sink, suppose this is a source, this is a sink, source temperature T1, this is T2, and here heat is flow. Here heat flows from sink to source. Here heat flow from sink to source. Suppose this is Q2, this is Q1, and if this is, as the temperature of the sink is less than source, so heat cannot flow automatically from sink to source. So a work has to be done by external agent, which is here a compressor. A compressor acts. A compressor works. So here work must be done on the system so that cold heat can flow from sink to source, because temperature of sink is less, and so here heat whose temperature is here gas whose temperature is less than this can flow from this to this. Okay, coefficient of performance. Coefficient of performance beta equal to output by input. Output energy here, output is input here is W, but output is what amount of heat extracted by the sink. This is the output. Output here Q2 and input here W. So Q2 equal to, we know here W is input, this and this enters here, W and Q2 enters in the system, and Q1 is output in this system. From this system this and this enter and this. So here W is in this system W is input, and here in this system W and Q2 is input and Q1 is output. So W plus Q2 equal to Q1, that is W equal to Q1 minus Q2. So if we put here Q2 by W equal to Q1 minus Q2, which is equal to, if we divide by Q2, 1 by Q1 by Q2 minus 1, which is equal to, always the heat ratio of heat is always the ratio of temperature. So we can write Q1 by Q2 equal to T1 by T2 minus 1. From this we get beta equal to T2 by T1 minus T2. This is called coefficient of performance. Now this is called beta. So relation between eta and beta. Eta is used in heat engine and beta is used in refrigerator. Coefficient of performance, efficiency, and beta is used for refrigerator, which is coefficient of performance. So to find the relation, we have to draw source. Temperature is T1, heat is rejected, so this is U2. This is a sink. Temperature is T2. This is for heat engine, and this is for heat engine. This is for heat engine, and for refrigerator, this is source T1. Just in refrigerator, direction of heat flow is reversed. So direction of heat flow is reversed, that is from this to this. This is Q2, Q1, and so a work is done on the system. So this is the diagram of refrigerator. This is the diagram of energy flow in refrigerator. This is the diagram of energy flow in heat engine. And so here efficiency equal to, we know that efficiency equal to 1 minus T2 by T1, T2 by T1. I proved that T2 by T1. So from this we get T2 by T1 equal to 1 minus eta. Now for coefficient of performance, beta equal to, we know coefficient of performance beta equal to output Q2 by W, which is equal to Q2 by W, Q1 minus Q2, which is equal to T2 by T1 minus T2. So if we divide T2 by T1, if we divide by T1, we get this. Now T2 by T1 equal to 1 minus eta. Now this is equal to 1 by eta minus 1. So beta equal to 1 by eta minus 1. So beta equal to 1 by eta minus 1. This is the formula. A ideal heat engine whose efficiency should be 1. An ideal heat engine. Now what is the different step of Carnot heat engine? Here you have to remember the 4 stroke. First stroke, First stroke is called isothermal expansion. Isothermal expansion. Second stroke is called adiabatic expansion. Third stroke is isothermal compression. Fourth stroke is called adiabatic compression. So in fourth step, one cycle is completed in Carnot engine. In fourth step, one cycle is completed in a Carnot engine. So this is an ideal heat engine. So the diagram of heat engine is same as Carnot heat engine. Now what is the diagram? What is the different parts of the Carnot heat engine to perform the cyclic process? What is the different parts of the Carnot heat engine? The parts of Carnot heat engine, parts of Carnot heat engine is that parts of Carnot heat engine is one is first a heat reservoir. Different parts of the Carnot heat engine is given mainly four parts. This is the source. Source is the petrol or diesel chamber where heat is produced. So source is always heat reservoir of large thermal capacity. Source means it produces the heat always. And second is insulating cylinder. A cylinder piston contain a cylinder piston is contained. Some gas is enclosed within the cylinder and piston is frictionless. This is the piston. Piston is frictionless and some loaded is added with the piston such that the gas can compress. Some load is fitted with the piston. This is piston is insulating piston and bearing some load. So this is the insulating cylinder. But the base is conducting. This base is conducting because when it put in the source such that the heat can enter into the gas. Third part is sink. Sink is also a heat reservoir but whose temperature is less such that it can absorb or it can take all the heat delivered by the gas. When some heat is rejected from this gas during compression, then the source can take this heat. So temperature of the sink is lower than the temperature of the source. And a insulating pad. What is insulating pad? Insulating pad means it is insulated such that no heat can exchange, no heat can transfer from inside to outside, or no heat can enter from outside to inside. So in adiabatic process, we know the definition of adiabatic process. We know where there is no exchange of temperature. So for adiabatic compression or expansion, in insulating pad that is insulated must be required to perform the process in adiabatically. So insulating. So these are the four main parts. Now how the ideal steps. First, isothermal expansion. First two step is expansion. Isothermal expansion, and second is adiabatic expansion. First two step is expansion. Now what happens? This cylinder piston is placed within the source so that the heat can enter into the gas. This is source. Source means heat produced here. Heat is entered into the gas. This cylinder is placed into the source. So the gas is expand. Gas expands isothermally. So when this cylinder is placed into the source, some heat enters into the gas. Now the gas expands isothermally expansion. That is as long as this cylinder is placed into the source, temperature remain constant. Isothermal means temperature remain constant at T1. Suppose temperature is T1. Now next step is adiabatic expansion. Now this gas is placed into the insulating pad. This cylinder piston is placed into the insulating pad, so that now as it is insulated, so no heat can exchange between system and surroundings. That is, heat cannot goes from the gas to the outside. So this is adiabatic expansion. No heat exchanged. So as no heat exchange, here temperature falls from T1 to T2. Now the third step is this is expansion, and third step is isothermal compression. Third step is isothermal compression. That is, now this gas, now the cylinder piston is placed into the source. Now this cylinder piston is placed into the sink, whose temperature is less. So as the temperature is less, now the heat enters into the sink. The source absorbs the heat. So the gas is compressed. As long as gas is compressed, but temperature remains same. So temperature is remain T2. Now fourth step is again this cylinder piston chamber is placed into the insulating plate once again. So when it is placed this way, now it is compressed, but it is adiabatically compression, because no heat now can exchange from source to outside. So this is from no heat is exchanged from gas to the outside. So this is adiabatic compression. And again adiabatic compression, again its temperature, as the compression takes place, again temperature goes to T2 to T1, such that its initial and final temperature remains same. So in four step total Carnot heat engine operates for one cycle. These are the four steps. Okay. Now so first process is, suppose from 1 it start. First isothermal expansion. This, suppose this is 1 point, this is 2 point. Then adiabatic expansion. Then adiabatic expansion. 2 to 3, suppose 3. Adiabatic expansion. Now next compression take place. That is, expansion means, so this step is, suppose this process AB to C. AB is isothermal expansion. Here volume is, suppose here state is T1 V1, temperature T1. Now isothermal expansion, so here pressure P2 V2, temperature remains same T1. Now it is adiabatic expansion, so here pressure is P3 V3 and temperature is T2. Now again here volume is increased from V1 to V2, and V2 to here expansion take place, so volume is increased from V2 to V3. Now this is called this is isothermal expansion. So now this is adiabatic expansion. Now compression take place. Now third step is isothermal compression. So isothermal compression, that is gas is compressed. So suppose this gas is compressed this way. Suppose C to D. This is isothermal isothermal compression. and from this to this D to A again. This is adiabatic compression. So these are the 4 steps. Now P1, P3, T3. This pressure is P4, volume V4, and temperature is isothermal, so T2. Again from this T2 to the temperature comes T1. So again these are the 4 cyclic process. These are the 4 cyclic process. This. These are the 4 cyclic process. So these are the graph. Now what is the work done? Work done from A to B, A, B, C, D. So if we draw now we have to write the work done in different process. Work done in different process. Work done. So AB is isothermal expansion. AB is isothermal expansion. AB. Work done in different process. Work done in different process. For process 1 isothermal expansion, work done equal to, for process 1 isothermal expansion, that is for curve AB. Curve AB. Work done equal to what? Work done equal to, we know, work done equal to nRT. T is temperature into log expansion is positive work done, so V2 by V1. Now V2 by V1 equal to, as P1 V1 equal to P2 V2, so V2 by V1 equal to P1 by P2. So this is the work done for isothermal expansion, or that is whose curve is AB. Work done equal to this. Now for BC, now for curve BC. Now curve, second step for curve BC. What is the work done? Work done equal to, this is adiabatic to NR expansion, so temperature falls. NR T1 minus T2 minus T1 by 1 minus gamma. NR T2 minus T1 by 1 minus gamma. 1 minus gamma. NR T2 minus T1 by 1 minus gamma. As T2 less than T1, so this is negative work done. For curve C to D, this is isothermal compression. Now the isothermal compression work done equal to NR T2 ln final by initial ln V2 by V1, that is V4 by V3, as V4 is less than V3, so this would be negative. So we use always nRT log final by initial, final volume by initial volume. We always use final volume by initial volume. Okay, so isothermal compression, or we can use this ln P3 by P4. P3 is less than P4, so this is also negative. For curve CD, that is isothermal compression, the work done equal to this. Next stroke is adiabatic compression, work done equal to NR final, here T1 minus initial by 1 minus gamma. So adiabatic compression T1 minus T2 by 1 minus gamma. This is the work done for adiabatic compression. Step work done equal to NR T2 minus T1 by 1 minus gamma. This is the work done for minus W3 by W1, which is equal to 1 minus Q2 by Q1. So from the different, we show that the efficiency becomes 1 minus P2 by T1. This is the formula of efficiency of Carnot heat engine. Same formula as ideal heat engine. There are three statements related to second law of thermodynamics. First is Clausius statement. Clausius statement states that it is impossible impossible to transfer heat from cooler body to hotter body. This is natural. Always heat spontaneously from hot body to cold body, but so it is impossible to transfer heat from cooler body to heater body, from cooler body to hotter body without the aid of an external agency. This is Clausius statement. Second statement is Kelvin statement. So it is impossible to build. It is impossible to build a heat engine that has 100% efficiency. This is Kelvin statement. And third statement is entropy. What is entropy? Entropy definition is dq by T, that is heat rejected or absorbed at by its temperature. Heat resolved. This is the ratio of heat resolved or rejects to the temperature of the body. This is called entropy. Actually, entropy is the measure of randomness or disorderness. Measure of randomness or disorderness. That is when molecule potential energy is less, potential energy of any substance less, then it randoms most. That is, entropy is more. Potential energy is it randoms most. That is, suppose a water is contained in a container. Some ink is dropped here. Now, when the ink molecule spread throughout the water, then its entropy increases. That is, disorderness or randomness increases. It is impossible for any system in a way that entropy is destroyed. Automatically, always disorderness be increased. This is no external work done is required. When we put some ink in a water, then automatically the molecule spreads. So here no external work done is required. When we put object at high position and it drops automatically, that is, water automatically flows from hill to the ground. Student, this is the end of the class today. To watch more important problem in the chapter thermodynamics, watch my another video. Okay, thank you.